Okay, here it is, lesson 4 of week 2, proposing catalytic cycles for palladium-catalyzed coupling reactions. These are extremely powerful reactions for organic synthesis, and we will also discuss CH bond activation at least a little bit later in the talk. There are 3 main classes of palladium-catalyzed coupling reactions that are in the textbook: Negishi, Stille, and Suzuki coupling. There is also there are other examples, but these are the 3 that we're going to focus on a little bit, but we're only going to go into the Suzuki reaction in detail. Let me remind you what I expect you to be able to do. I expect you to be able to name the elementary steps if they're given to you in a catalytic cycle, or if you're not given the cycle, to propose reasonable steps that make sense for a reaction. So how do you do that? Well, you look at the catalyst identity, remembering that often what you add to the reaction is not the active catalyst, but it needs to be converted into an active catalyst by some sort of transformation. We saw that last time with the cobalt catalyzed hydroformylation reaction. Identify the catalyst using the CBC notation: ligand bond number, valence number, DN count, valence electron count. So identify what you've got and what reasonable steps you could take given the other reagents present. And of course, remember, it's all equilibrium, and if you get stuck somewhere, you can always Le Chatelier your way backwards and try a different chemical reaction. Students over the years have proposed some bizarre chemical steps that we have not seen in class. I want to remind you again, let's focus on using steps that we've seen in class. So oxidative addition, reductive elimination, 1,1 or 1,2 insertion. The reverse of that, elimination or deinsertion chemistry. Those are steps that you could do. The beta hydrogen elimination is a specific case of an elimination reaction. You can also do ligand substitution reactions. You can do a rearrangement. So if you know that you need to have your substituents cis in order to do a nonpolar reductive elimination, then you can rearrange your complex to make them cis. And redox, which we probably won't see much this year, and 2+2 cycloaddition, which we will not see this year at all. I want to go through some earlier coupling reactions just to show how important the Suzuki coupling is. So the Negishi coupling was a coupling reaction that allowed you to couple an aryl or alkyl halide with a zinc reagent. The side product is a zinc salt. The details of this mechanism are not known with a lot of certainty. Rate limiting step is transmetallation. None of this is super important for this year, but what I want to point out is the disadvantages of this reaction. The alkyl zinc reagent is extremely water sensitive, so alkyl zincs need to be handled under rigorous air exclusion techniques, moisture exclusion techniques. And if you don't do that, you lose your alkyl zinc reagent and you get no coupling reaction at all. So you can do this reaction. It's a powerful reaction, but it's a little bit tricky and a little bit hard to do. The Stille coupling was an improvement on that reaction. So you could take an RX and a alkyl stannane. It turns out that the methyl groups transfer much more slowly than other groups. So if you have like a butyl trimethylstannane or something like that, you can transfer the R group faster than the methyl group. But tin reagents are extremely toxic. They are air stable, so it removes one of the considerations, but the reagents and the side products are both toxic, so we want to minimize their use. And so that brings us to the Suzuki coupling. This couples an RX with an alkyl boron reagent, and the side product is boronate ester. So boron reagents are relatively non-toxic. These are air stable. We do these reactions in air. Sometimes we'll blanket them with nitrogen just because I feel better when you do it. But these are really easy to carry out. And so we can do all sorts of different things. This reaction has been very extensively studied, and I'm not going to go into the details of the organic chemistry behind this. I just want to focus on the palladium. But one important step that's done is the palladium halide that, when you first add the RX group, you make a palladium halide group. You add an alkoxide to make the palladium alkoxide reaction, and that promotes the transmetallation step. Now, I haven't explained what the transmetallation step is yet, so let's go to the next slide and go through the Suzuki reaction and see what the steps are. Okay, we're going to start here with sort of a generic palladium zero catalyst, and specific catalysts are widely varying depending on the exact reaction you're trying to study. Different phosphine ligands, different co-ligands, different alkoxides have different features. In general, they're palladium phosphine compounds. So palladium triphenylphosphine is a good starting material for this reaction. And the first step is addition of this R2X onto the palladium. It sure looks like an oxidative addition. We've gone from palladium 0 to palladium 2. The coordination number is not specified here, but it's 2 more in this complex, so it's definitely an oxidative addition. We can then do the transmetallation. This X group is transferred into an OT butoxide by adding sodium T butoxide, removing sodium X, which precipitates out of the solution. This now is set up to do the transmetallation with the boron reagent. It turns out the sodium T butoxide also activates the boron reagent itself to make this anionic boron salt, which is much more reactive, and it allows the R1 group to be transferred in place of where the T butoxide is. And so you get this R1, R2, palladium 2. To close the loop, we've got to get back to palladium 0. That's a reduction. And we've got to eliminate our new carbon-carbon bond. We do a reductive elimination to get to the new product. So there are the steps labeled: oxidative addition, activation, transmetallation, and reductive elimination. We've started doing Suzuki couplings in my laboratory over the last year and a half. So this is just one of the reactions that we do. We can start with this diiodoaldehyde or the dibromoaldehyde. It really doesn't make that much of a difference. We're using palladium tetrakis triphenylphosphine as our pre-catalyst. We're adding this boronic ester in the presence of sodium carbonate as a base, and we can couple this aryl ring onto the aldehyde aryl ring to make a variety of different substituents. We can then couple this aldehyde in a second step onto this amine group to make ligands, and these are the chiral ligands that my students have been working on over the last 2 years. This reaction is so easy to do, well, this first reaction, the Suzuki reaction, that Chem 40 students, the first year laboratory research students, have been carrying out this reaction. They're the ones who actually did it first in my lab. And then last summer, Emily Falk, Veronica Sho, and this year, Emily Shimizu have been carrying out this reaction a large number of times to make these aldehydes. This is a slide that was going to be presented at the ACS meeting that was canceled, and they will obviously not be working in my lab this summer because we're not having a summer research program, but if they were, we'd still be doing it this coming summer. Okay, switching gears quite a bit, CH bond activation. If you think about it, hydrocarbons have a lot of CH bonds. It's the most common organic functional group, but we don't tend to think of it as a functional group because they don't have a lot of reactivity. You can't really do a lot of chemistry with a CH bond. We burn them. These are fuels. Gasoline is a hydrocarbon. And if you remember back on the fuels unit from Chem 23A, especially if you were in my class, there's a day or two where I got up on my soapbox and talked on and on and on about the conversion of methane to methanol. Methane is a gas. It is a contaminant in oil fields. And instead of capturing it, because it's a gas, it's hard to transport and store, we actually just flare it off. And so when you look at an oil rig or refinery and you see the flare coming out of the top, we're just burning the methane, contributing to CO2, global warming. If we could convert one of these CH bonds into an alcohol and make methanol, that's a liquid fuel. We're set up in a liquid fuel economy now. We could totally do this. That's a huge holy grail of the field, is to specifically convert methane to methanol. There are many other ways to solve these types of problems, but that's the one that organometallic chemists have looked at the most. The text discusses directed CH bond activation, so you can construct a ligand that allows the metal to sort of bind to the substrate and activate one CH bond but the holy grail is the selective undirected CH bond activation. So the first report of that was published that converted methane to methanol was the Shilov system, which was published in 1987. So this reaction takes a platinum complex, so platinum dichlorodiaquo, and that actually reacts with methane to form this compound. I encourage you to do the electron counting on this to verify that this oxidative addition reaction makes sense, but clearly we've activated the methane and turned it into the methyl hydride. And then a chemical reaction takes place. We're losing HCl. It's a reductive elimination, and we can form the methyl chloride complex. This then reacts with an external oxidant which basically delivers the two chlorines. So we've oxidized the platinum here from platinum 2 to platinum 4. That is a high oxidation state, and so the platinum wants to do a reductive elimination, and what it does instead of the reductive elimination is attacked by an external water. So you can imagine the lone pair on this water hitting this methyl group, this bond going to the chloride. And so we make methanol and we make HCl as the other product, and we then get down to our platinum dichloride diaquo complex. So this is catalytic in platinum 2, but if you've been paying attention, this is stoichiometric in platinum 4. Any reaction that you propose that's stoichiometric in platinum to make a simple hydrocarbon doesn't seem to be very efficient or cost effective. And it's not. This is not a commercially viable reaction. Using platinum to make methanol doesn't make a lot of sense, but it certainly launched the field, and people have really studied this, trying to figure out new ways to exchange the oxidant. This is the only step that we really need to change, because the other platinum is catalytic. So this platinum keeps cycling around. We need to figure out a different oxidant. About 10 years later, the catalytic system was discovered, and this reaction is very similar. So you take a platinum compound with this sort of a bipyridine type of a ligand and these two OPs. The P is hydrogen sulfate or chloride. So it's a counterion, and this loses one of the OPs to get into this system. You can add methane and lose HOP, so oxidative addition and reductive elimination to give us our methyl compound. Then we oxidize it, and in this reaction it's oxidized using SO3 to SO2. This is a masked sulfuric acid. You give off SO2 gas. You get this product, which then does the reductive elimination, regenerating our starting catalyst. Okay, this seems like a great reaction. We've replaced our stoichiometric platinum oxidant with a stoichiometric sulfuric acid oxidant, much cheaper. But this reaction has to be run in fuming sulfuric acid. It's a pretty nasty solvent to work with. And I didn't emphasize this, but you notice this product is not methane. It's protected methane. It's methane sulfonate. And that's extremely difficult to remove from the reaction mixture. And then you'd have to deprotect it. So you've added several steps, a purification step, a deprotection step. And so this was a very exciting reaction. Unfortunately, it's still not really gone anywhere, and we still need to work on solving this problem of taking methane and turning it into methanol. So maybe one of you will, who are listening to this video, go out and solve this problem for the rest of us. So that's the end of week 2, organometallic chemistry. Next week we're going to begin our study of bioinorganic chemistry.